Hello, my name is Charles Taylor. In the statistics group at the University of Leeds, and in this session we're going to talk about the normal distribution, really just an introduction to the topic. So firstly we'll look at the normal distribution as a model for continuous data. And I've drawn here a histogram of chest measurements of Scottish militiamen taken from about the middle of the 19th century. There were about 6,500 Scottish militia, and each one has a chest measurement recorded, and here we have a histogram of the results. And we can see what's quite a characteristic shape of this sort of bell-shaped curve. And many data sets have a very similar picture when you draw a histogram. In particular, those data sets which are based on physical measurements like length or height or weights or temperature or time, all these ones could have very precise measurements where you record them to lots of decimal places. And so we can think of those as being on a continuous scale. But of course, very often, the data is just recorded to a discrete set of points. So you might measure to the nearest centimetre, or to the nearest inch, or you might measure to one decimal place. And so the records of the data can appear to be discrete, even though the measurements themselves are technically on a continuous scale. And so in this data set, these measurements were actually measured to the nearest inch. And so this resolution of the histogram is as fine as we could get. And of course, although we can use the normal distribution for continuous data, it also serves as a very good model for some discrete data sets. So for example, if you measure your performance on an exam, usually recorded as a percentage, then although those numbers are usually integers, we can still use a normal distribution as in most cases, an adequate approximation to the data. So strictly speaking, it's for continuous data, but can often work for discrete data. And of course, at the end of the day, we're interested in whether it's a good approximation, not necessarily whether it's an exact or technically accurate value. And here's a curve drawn on the picture just to show what a normal distribution would look like if the data were exactly normal. And you can see some slight deviations here, but to the first approximation, it's really looking quite like a normal distribution. So what are the properties of the normal? Well, the normal distribution depends on two numbers, two constants. And we use Greek letters for these usually. So the first of these, mu, is a Greek m, and the second one, sigma, is a Greek s. And the value of mu shows where the distribution peaks. So here's a picture of the normal distribution, and this has a peak at the value 0. And so in this case, mu is 0. So the value of sigma controls the spread. So first of all, let's see the change in the curve as we change the value of mu. So this just moves the curve. It leaves everything, the height the same, just moves it to one side by 2 units. So the mode, or the peak of this distribution, has moved to the value 2, and the value of sigma is unchanged, still takes the value 1. If we take another pair of curves, so the start point again is with mu equals 0 and sigma equals 1. In this case, we've changed the value of sigma, and you can see the effect of spreading out the curve. And at the same time, the height has been decreased. So the height, in fact, is now half of what it used to be, about 0.2. And that half is the inverse of the multiplier in the value of sigma. So sigma's gone from 1 to 2. The height has gone from 1 to half the value it was previously. And so there's a whole family of these curves. You can change mu, which essentially is sliding the thing backwards and forwards, or you can change sigma, which squashes it down or compresses it up into a more vertical stripe. And you can imagine an infinite variety of such curves, each one characterized by this pair of mu and sigma. Well, what are the properties of all these curves? Well, first of all, it's worth noting some standard shorthand notation. And what we use are these two numbers, mu and sigma, are put into brackets, and we have the letter n in front to show it's a normal distribution with these two parameters, or two numbers, mu and sigma squared. And it turns out that mu, which is the middle point of this is the mean of the distribution, and sigma squared is the variance. And so sigma, which controls the spread, is then the standard deviation, the square root of the variance. Okay, so the properties to remember, and some of these you almost have to learn. First of all, the area under any normal curve, that's for any values of mu and sigma, the area under the curve is exactly 1. Secondly, as you can see in the pictures, the curve is symmetric about the value mu. So a mirror image, or if you flip it over, you get exactly the same picture, and it's symmetric about that point. Thirdly, although we said it was a bell-shaped curve, most bells we've ever seen have an end point to them, and that's not true of this curve. It actually extends to infinity, or indefinitely, in both directions. And as it does so, it gets very, very close to the horizontal axis. But although it extends a long way in both directions, we don't have to go very far before we've captured nearly all the area. So remember, the total area under the curve is 1. And if we go just 3 standard deviations in both directions from mu, we actually get nearly all the area. So 99.7% of the area, approximately, lies in that interval, or the range, from the middle of the spike minus 3 standard deviations to the middle of the spike plus 3 standard deviations. Well, we've got this big family of curves. There's one special one called the standard normal distribution. And we refer to this quite a lot in our calculations for reasons which will become clear in a moment. So for continuous data, we need to know about areas under the curve in order to calculate probabilities. So for example, if a random variable x has a normal distribution with mean mu and variance sigma squared, then the probability that x takes a value within a certain range between values a and b, that probability is computed as the area under the curve between those two limits. So here's some pictures which show typical areas under the curve we might be interested in. So on the left curve, left of the panels, we have the normal distribution in black, which has mean 0 and standard deviation 1. And the black shaded region would be the area under the curve where x is bigger than 1.5. And you can see as we slide the curve up to the right in the red picture, which has a mean of 2, then that area is exactly the same as the area under the red curve where x is bigger than 3.5. So you can see the effect of translating the curve is equivalent to or corresponds to a shift in the values of a and b. On the right-hand side, we have the examples where the standard deviation has changed. And the red curve here, if you remember, has a standard deviation of 2. And it turns out that the areas in the right-hand side, the black area and the red areas, are exactly the same amount. And both correspond to a probability of x in its corresponding distribution taking a value above a certain amount. And the equation here sums up what we need to do to make these things equivalent. And it's a property which is called the normalizing of a random variable. A very useful property in which if x is normally distributed with any mean you like and any standard deviation or variance you like, then if we subtract the mean and divide by the standard deviation to get z, this equation down here, then this transformed value has a standard normal distribution. So the mean is 0 and the standard deviation is 1. So the standard normal has mean 0 and standard deviation 1. And if we do that, then if we want to work out an area for a general x, so if x has a general mean and standard deviation, then the probability of lying between two values of a and b, we simply apply the same transformation to the endpoints. So all we've done from this equation is subtract the mean and divide by the standard deviation over all 3 components. The middle component then becomes z, and the n2 components are transformed by the same transformation. And so these two statements, this kind of 3 lines in the middle there, just says these two statements are equivalent. The probability of x being between a and b, where x is a general normal, is the same as the probability z lies between a minus mu over sigma and b minus mu over sigma, where z is a standard normal. Now this statement, of course, is only true provided sigma is positive. So that's an important thing I've omitted to say, is that the standard deviation is a positive quantity, as it is when you analyze or summarize a data set. For a distribution, it's not going to be negative. Okay, so mu equals 0 and sigma equals 1 corresponds to the standard normal distribution. And in this case, we write often with a z to show it's special, is distributed as a normal distribution with mean 0 and variance 1. Of course, 1 squared equals 1, so we don't bother putting 1 squared there. And to obtain probabilities, we need to find areas under the curve. So what we would do, if we were working from scratch, is to try and do it by integrating the function of the curve between the two limits. So the function of the curve is given by this, at first sight, it looks a quite complicated formula, 1 over the square root of 2 pi times e, or the exponential of minus a half z squared, and we integrate that over z between the limits a and b. Remember, the area, total area under the curve is equal to 1, and so for certain values of a and b, we could work it out. So if a was minus infinity and b was plus infinity, then we'd know the answer, but that's not usually very interesting. It's actually very difficult to do this integration analytically, and we'd have to use numerical methods, for example, the trapezium rule, if we're going to work it out for ourselves. But fortunately, there are lots of tables which actually do the integration for us, and it turns out to be much simpler by the use of tables than it would working it out by scratch with the trapezium rule.